So next topic is lightwave system. A lightwave system is nothing but an optical fiber communication system. It's just a name, another name for fiber optic communication system. So what you have in a lightwave system, we'll have an optical transmitter, we have a communication channel. Our communication channel is nothing but an optical fiber, and we have an optical receiver. So the function would be, we'll have an input. The input can be in any form, electrical form or any form. So this electrical or any form input signal has to be converted to our optical form. That process is done by our optical transmitter. So this optical signal is then transmitted through our communication channel or our optical fiber to our optical receiver. The function of our optical receiver is to convert the signal back from this optical domain to whichever domain it was obtained in our input side. So thus we receive our output signal. So while designing the light wave system, the optical transmitter and optical receiver play an important role. So from the architectural point of view, the light wave system can be classified as 1. Point-to-point link, 2. Distribution networks, 3. Local area networks. So the first type of light wave system is point-to-point link. Point-to-point link, as the name suggests, we have 2 points and we are connecting the 2 points. That is a point-to-point link. That means we have a transmitter and we have a receiver and we have a direct connection. That is a point-to-point connection between the transmitter and the receiver through our optical fiber. Thus we receive a point-to-point link optical fiber communication system, and this link length can vary from less than a kilometer to thousands of kilometers. If this link length has a greater value, like the link length exceeds a certain value in the range of from 10 to 100 kilometers, then we need to compensate for the losses that takes place in our optical fiber. To compensate for these losses, we'll be using two techniques. One is with the use of regenerators, and the other one is the use of optical amplifiers. These regenerator is nothing but a optical transmitter receiver pair which has the capability of replicating the signal. Similarly, we'll be using an optical amplifier. The optical amplifier amplifies the optical signal. So from the figure you can see the two types of process that are being used for compensating the losses. One is with the use of regenerator, the other one is the use of amplifier. As I already mentioned, the regenerator is a receiver transmitter pair. Whenever we are receiving an optical signal from the transmitter to the regenerator, the receiver in the regenerator converts this optical signal into electric signal, and this electric signal is then converted back to optical signal by the transmitter. So what we are doing with this regenerator is that we are repeating the signal, thereby compensating the losses or the fading of the signal that can takes place. Next one is optical amplifier. The optical amplifier doesn't require any domain conversion, that is converting the optical signal to electrical signal like in the regenerator. It doesn't require any domain conversion. It can directly amplify the optical signal that is being fed into the optical amplifier. So through these two techniques we can compensate for the losses that takes place in a point-to-point link. So the spacing between these regenerators or optical amplifier is called repeater spacing, and it is denoted by the letter L. And this repeater spacing L depends upon the bit rate. The bit rate is nothing but the rate at which the information is transmitted through our optical fiber communication. This bit rate depends upon operating wavelength. The product of bit rate into repeater spacing, that is the product BL, is a measure of system performance in point-to-point link. So in order to measure the performance of a point-to-point link communication system, we'll be evaluating the product BL. Okay, since the bitrate depends upon the wavelength, operating wavelength, the product BL will of course depend upon the operating wavelength BL. So other type of losses that takes place in a fiber are dispersion and attenuation. Because of the bitrate, there can be dispersion in a optical fiber, bitrate related dispersion. Also related to the length, we have other loss called attenuation. This is the block diagram for a point-to-point link. As you can see, we have direct point-to-point link between each of the blocks: the information source, the optical transmitter, optical receiver, and the user. So the simplest form of a point-to-point link is a simplex. That is, the information is transmitted in one direction. So to analyze the performance of a point-to-point link, the parameters or the key parameters that we use are the transmission distance, the channel bandwidth, and the bit error rate. By evaluating these three parameters, we can analyze how good is the point-to-point link communication system. So the next topic of discussion is what are the factors as the system engineers should consider while designing a point-to-point link communication system. When a system engineer is designing a point-to-point link communication system, the three factors that he must consider while designing it: what type of optical fiber he should choose, what type of optical transmitter, or what are the different things that require an optical transmitter that he has to design, and which type of optical receiver and the parts associated with it he should be choosing. For that, let us consider the first condition: optical fiber. What type of optical fiber he'll be choosing? He'll be choosing a single mode fiber or a multi-mode fiber. If he wants a short distance communication system, then he should go for multi-mode. If he is looking for a long distance communication system, then he should be looking for a single mode. Then core size is another factor which determines which type of fiber he should be choosing. The refractive index profile of the optical fiber is another factor, and the attenuation and dispersion of the fiber is other factors that the system engineer should be consider when he is choosing which type of fiber he is selecting for his point-to-point link optical fiber communication system. So the next one is optical transmitter. So which type of optical transmitter or optical source he'll be using, like a LED or a laser? What is the operating wavelength? What are the output and emission patterns? What type of modulation he'll be using? What type of modulators he'll be using? What are the type of coding? So these are the factors the system engineer should consider before designing our optical transmitter. And the next one is an optical receiver. While designing an optical receiver, he should be considering what type of optical receiver he'll be choosing, a pin diode or avalanche diode. What are the responsivity? What is the operating wavelength? Operating wavelength should be considered both at the transmitter and the receiver. And what of the demodulator he should be using, the decoder. All these things should be considered while designing an optical receiver. Okay, so distribution network is another form of light wave system. We have already discussed point-to-point link. The other one is distribution network, and we have one more type of light wave system, that is local area network, that we'll discuss in the next slides. So in distribution network, as you can see here in this communication system, we have a central hub and we have different subscribers or different channels. From these hub, we transmit or distribute information through these optical fibers. These optical fibers serve as the link between the different hubs and the different channels or the subscribers. The different topologies that are being used in a distribution network are hub topology and bus topology. So in the hub topology, we have a central hub, and from the central hub, we will be routing the signal to different channels of the subscribers. The other name for hub topology is my metropolitan area networks. Why this name? Because we will be placing hubs across all the metro cities, and from this hub or these metro cities, we will be transmitting data to all the channels across the city. Next is the bus topology. In bus topology, as you can see, a single optical fiber carries the information across the channel, and for all the subscribers, we'll be tapping out the signal with the help of optical tabs and transmitting the signal. The bus topology is very clear from the diagram, as you can see in the previous slide. So the other type of a light wave system is local area network. Local area network is that communication system used when we have a group or where we have a network where we require continuous transmission of information to and fro in a random manner. like in the case of universities, campuses, offices, hospitals, where we require continuous transmission of data to and fro between different clients or different people. In such type of communication systems or networks, we are using local area network. One difference of local area network from the metropolitan area network is that it provides a randomness to the subscriber. The different topologies that is used in local area network is bus, ring, star. Okay, so you can see the different topologies in the next slide. So this is the two topologies that are being used in local area network. One is a ring topology and the other one is a star topology. In ring topology, all the nodes or all the subscribers are connected in a ring fashion through the point-to-point link, so that each of the nodes have a transmitter or receiver pair. That is, each subscriber has a transmitter or receiver pair. Each of these subscribers are also called as nodes. Okay, so each pair is a transmitter receiver pair. That is, it can transmit and receive information at the same time. That is, it has a randomness here. The other one is a star topology, in which the nodes are connected in in a star fashion, and the central node acts as a server node, which helps in switching of data to and fro between the different subscribers or the nodes in a random fashion. So the advantages of a lightweight system is a long transmission distance, large information capacity, small size and low weight, immunity to electrical interference, enhanced safety, and data security. So long transmission distance, as we all know, the optical fiber has very less loss when compared to our conventional copper cables. Hence, due to this important property of less loss, we can transmit signals a long distance through optical fiber communication system or this lightweight system. Other thing is large information capacity. As we all know, optical fiber has a huge bandwidth, so the information carrying capacity is high. Next is small size and low weight. As you all know, the optical fiber is made from silica glass threads. So it is very small in size and it has very low weight. Next is immunity to electrical interference. As already mentioned, the signal is transmitted in the form of light in optical fibers. So it doesn't have any electromagnetic interference like we have in our conventional copper cables, which the electrical signals create. Next is enhanced safety. The optical fiber has a buffer coating on the buffer jacket, which secures the information that is being transmitted to our optical fiber, and also it is immune to sparks and other high potential voltages. Now the next one is data security. It provides a high data security because the tapping of signals to an optical fiber is not possible, and also we are transmitting signals in coded form, and decoding of these signals is not very possible for the eavesdroppers unless or otherwise that code is attained.